Welcome to Data Science with EJD. We continue with clustering under unsupervised learning under machine learning. Like we know already, machine learning is that arena where uh, machine learns from data. But then machine learning is divided into supervised and unsupervised learning. Supervised learning is that place where machines learn from labeled data, while unsupervised data, you have unlabeled data. And when we talk about labeled data, we're talking about having inputs and outputs. You have some features leading to determining a particular target. But in the case of unsupervised learning, you have unlabeled data where all you're getting from the data after you're done is some pattern, some categorization, and things like that. And so talking about supervised learning, we have some particular algorithms like clustering, dimensionality reduction. So we are still talking about clustering. Before now, I've talked about k-means clustering, and I went ahead to use k-means clustering to demonstrate customer segmentation, such that if you own a business and following the pattern of how people buy from your business, you can actually know how to target specific groups based on the clustering that has been done. So in this video, we move to something higher, talking about hierarchical clustering. So, introduction to hierarchical clustering. It is an unsupervised learning method used to group data into a hierarchy of clusters. Unlike partition-based algorithms like k-means, hierarchical clustering does not require pre-specifying the number of clusters. Under k-means clustering, we needed to, find a way of getting the number of clusters using things like the elbow method or the silhouette score to know the highest number of, the optimal number of clusters that we should get from each data set. But in the case of hierarchical clustering, that is not necessary. So, like partition-based algorithms like k-means, hierarchical clustering does not require pre-specifying the number of clusters. Instead, it builds a tree of clusters known as a dendrogram, from which an appropriate number of clusters can be chosen by cutting at a desired level. So here, the key thing is a dendrogram. So the key thing in under k-means is to determine the number of clusters you should have, especially the optimal number of clusters. I guess I want to break this up bit by bit. Let's see, this goes and then this follows, and then we have that. All right. So let's talk about types of hierarchical clustering. Hierarchical clustering is categorized into two main types based on the direction of construction. So we have agglomerative clustering, but that requires bottom-up construction. It is the most common type, and it starts with each data point as a singleton cluster. So you have a data point as a singleton cluster. At each step, the two closest clusters are merged. So it's like you're accumulating things and it's building up like that. The process continues until all points are merged into one big cluster. That is agglomerative clustering. It starts with one data point and merge it with the nearest, and then that becomes one cluster, and then you merge it with the next one, and it keeps going like that. So this is represented by a merging dendrogram. Then the algorithm steps involve first of all, you compute a distance matrix for all pairs of points. Then two, you identify the two closest clusters and match them. Then three, you update the distance matrix using a linkage method. Step four, you repeat steps two and three until one cluster remains. So it's more like in biology, what we call is it fission? Two cells merging together. They are, I think it's fusion, fusion. So two cells merging together, they are fused together. Then apart from agglomerative clustering, we have divisive clustering, which is top down. So this is less commonly used due to higher computational cost. So this one starts with one large cluster containing all data points. So instead of agglomerative, where you start with one data point and build the whole thing into the whole data set, then this one starts with the whole data set, and then you recursively split clusters into two at each step. So it's basically the opposite of agglomerative clustering. And this continues until each observation is in its own cluster, represented by a splitting dendrogram. Dendrogram. So for agglomerative, you have a link, you have a merging dendrogram. While for divisive clustering, you have a splitting dendrogram. And the more common one in use is agglomerative clustering, which is bottom up. So the algorithm steps, number one, you start with all points in one cluster. Then two, you use a criterion, e.g. something like you use dissimilarity, for instance, to divide the cluster into two. And then you repeat the process recursively on each derived cluster. So let's talk about linkage methods. How do you cluster things up? I think that's the idea of linkage method here. So the linkage method determines how the distance between clusters is computed when deciding which clusters to merge or split. So we have three different linkage types here. We have more than that actually, but more three of them are discussed here. You have the single linkage. Here, the distance between nearest points the description is about the distance between nearest points in the clusters. So D of AB, that's the distance between A and B, is the minimum of all A in A and all B in B, such that you have distance between A and B. So the shortest distance between nearest points between 2 points, I mean. So you can form long chain-like clusters. Then you have complete linkage, the distance between farthest points in the clusters, that's complete linkage. So the formula is given right there. So DAB is the maximum distance between A and B, such that every point in A and every point in B, you take their distance. So this tends to produce tight, compact clusters. Then you have average linkage, the average distance between all pairs of points. So the distance between A and B is actually equal to 1 over the absolute value of A over 1 over the product of the absolute value of A and absolute value of B, and then you sum up those distances. So you're averaging out the distances like what the description says, average distance between all pairs of points. So you take all pairs of points and you average everything out. So in this case, you have a balance between single and complete linkage. So there are other methods like the Watt method, which minimizes the total within cluster variance. And you have the centroid linkage, which uses the distance between centroids of clusters. Now let's talk about some distance metrics. The distance metric defines how the dissimilarity between two individual data points is measured. So you have common metrics like the Euclidean distance, which is the most commonly used for numeric data. Then you have the Manhattan distance, which is suitable when features are on different scales. Then you have the cosine similarity, which is often used for text or high dimensional data. So cosine similarity is one big metric that is used in natural language processing because it's basically for for text. Then you have correlation distance, which is suitable for time series or gene expression. In Python, scipy.cluster.hierarchy.linkage, you can specify the metric as a parameter. Now let's talk about visualizing clustering. We've been talking about dendrograms. You know, here you're visualizing clustering and talking about dendrograms. A dendrogram is a tree diagram frequently used to illustrate the arrangement of the clusters produced by hierarchical clustering. And the components of a dendrogram, you have the leaves, which represent the individual data points. These are the leaves. Then you have the branches, which indicate merges or splits of clusters. Then you have the height, which is the y-axis, and that represents the distance or dissimilarity at which clusters are merged. And how to use this? To form clusters, you cut the dendrogram horizontally at a specific height. The number of vertical lines the cut intersects gives the number of clusters. Now, working with real data set, we've worked a lot with the iris flower data set, and the summary of that data set is this. We have 150 observations, and that is grouped into three species of iris flower, Setosa, versicolor, and virginica. And there are four features measured. We have the sepal length, sepal width, petal length, and petal width. So let's talk about the code implementation in that situation. First, let me do the view well so I can let me show line numbers. Right, view, then line numbers, and we go to the code. Yeah, here. So for the code implementation, of course, you load the iris data set from the sklearn data sets. Then from the hierarchy, we need the linkage, we need the dendrogram, and we have the F cluster. Then we need to visualize using matplotlib. And then the metrics here, we adjusted rand score. So that is how you measure the cluster in this particular situation. Then you load the data. Iris is load iris, X is iris dot data. Talking about the here we have some kind of that's like, of course, we're doing clustering, so we shouldn't be worried about inputs and outputs. But I mean, for some reason, we have X equals iris dot data and Y tree is iris dot target. So you apply agglomerative clustering with different linkage types. So for method in single, complete, and average. So so we have single, what we just described now, single linkage. Yeah, types. This talks about types of linkages. So for method in single linkage, complete linkage, or average linkage, it says Z equals linkage, X method equals method. So you're going to run across all this. Then plot the dendrogram here, the dendrogram. So that has its own name. So you have dendrogram Z, truncate mode is none, labels is Y true. Okay, yeah, this is why we need the Y true now, the target. You have that. Then you have the dendrogram using whatever method that is chosen here, and then you have the linkage. So we're going to have dendrogram for single linkage, complete linkage, and average linkage. And on the x-axis, we have the sample index, while on the y-axis, we have the dissimilarity. So, and for each one of them, we are going to extract flat cluster. So the predicted Y, you have F cluster Z, T equals 3. Criterion is max cluster, targeting 3 clusters. So you evaluate clustering. So you, of course, like I told you, when you see any number like this, change the number and see the effect that has on the code. Then you're also now going to evaluate with ARI. You remember ARI is this adjusted rand uh, score. So ARI is adjusted rand score, Y true, Y pred. So that tells us uh, how powerful each method is. So I run this now, and then it takes a bit of time and we start getting the results. So it's still running. When you see the star, it's running. And then, yeah, so the first one, we have the dendrogram using single linkage for iris dataset. So we have it going this way, right? And in this case, the adjusted rand index, that's what's used in judging the hierarchical cluster. This one is 0.564. And then when you come to the complete linkage, which has been described before, that takes the distance, the farthest distance apart, right? The single linkage takes the minimum distance between 2 points, between two data points, while this one takes the maximum between them. And this gives a better score of 0.64. So the efficiency is like 64%, while the previous one was 56.4%. Whereas when you come to the average linkage, which averages out the single and complete linkages, so here the score is even better. You have like roughly 75%, and then you have the clustering coming out in this kind of way. So that's what you have there. So the dendrogram gives insight into the natural grouping of the data. So here, say what the grouping looks like. So it's looks like two main clusters, so to speak. That's what it looks like. And here you have uh you know you have the subdivisions going on like that. Um then you have this. So the dendrogram gives insight into the natural grouping of the data. The adjusted rand index evaluates how well the clustering corresponds to true labels. So ARI of 1 is perfect match, while ARI of 0 is random match. So the best of what we have here, as far as this iris data set is concerned, is the average linkage. That gives us the highest adjusted rand index. So choosing number of clusters, you can determine the number of clusters by cutting the dendrogram at a height where there are large vertical jumps, known as the elbow method. Using SciPy or cluster or hierarchy or F cluster with criterion max cluster to set the desired number of clusters, and criterion is equal to distance to set a dissimilarity threshold. So just like I said before, we chose 3 here, basically, and that's what led to all these things we got. So what if this T is, say, if I make it 2, let's see how that works. Now it's 2. Uh, okay. Now this is what we have still. Does it look like there's any kind of difference? Okay, yeah. I mean, 2 has made the ARI values very low. So it means we probably have maybe the more the cluster, the better. Now I'm making it 4. Let's see what the scores look like. So 56.2, 58.9. This is 72.9. Now you see that the performance with 2 clusters, with 3 clusters is better than two clusters and four clusters. So it means there's actually an optimal number of clusters you should have in this situation. So three clusters is giving us a better result than either three or four, right? So that goes. So choosing the number of clusters, that's what we've talked about now. What about the advantages and disadvantages of a hierarchical clustering? So no need to predefine number of clusters. That's one advantage. Disadvantage, computationally expensive for large data sets. So if you have large data sets and since you're merging data points in twos, that can be computationally intensive. Then Dendrogram provides interpretable results and it is sensitive to noise and outliers. That's one disadvantage. And then this another advantage is that it can capture nested clusters. So we have, if you look at this now, you have clusters of clusters. Like if you know this cluster now is a cluster of these two main clusters, and each one of them have some clusters under them. So you can have clusters of clusters. Something maybe I don't know if I can call it meta clusters. So the choice of linkage method affects the results. So you can see we got different results for simple, complex, and average linkage. And in summary, the feature you have the starting point for agglomerative. Each point is a cluster is a starting point for agglomerative. For divisive method, for divisive clustering, that is, the starting point is all points in one cluster. Then the process you match closest clusters for agglomerative and split based on similarity, the similarity for divisive. Output, you have tree of merges bottom up, and here you have tree of splits top down. Then common use, agglomerative is frequently used, while divisive is rare due to computational cost. Visualization to use dendrogram for both of them, but agglomerative is the most used, so that's what we get to see. So with this, we come to the end of this idea about hierarchical clustering, you know, and talking about the single, complex, complete, and average linkage like that. And we see that average linkage seems to do better. In the case of Iris dataset, you may want to try for other datasets to be sure. And of course, use the ARI score to know which performs better. That is the adjusted RAND index, like that. So let me know how helpful this video is for you. If you have subscribed already, thank you so much for that. If you have not, go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. And you can click on join to see I have membership on the channel now. You can check out the perks if you want some extra privileges as a member of the channel. You want to check out, there are 3 levels of membership right now which you can join. So feel free to do that. And be sure to like and share the video so that more people can have access to this great content I have going on here. So like come your way again, keep doing data right. Bye.